Jaswinder Kaur and I'm here to teach complex analysis, and our ongoing content is contour integration. This assignment 7 is very important and expected one. Very important. Let's start. The example is prove that the integration from 0 to infinity dx over x square plus b square the power n plus 1 is equal to pi over 2b the power 2n plus 1 2n factorial over n factorial square, where n belongs to the natural numbers and b is positive, strictly positive. Let's solve this. We have to integrate f of z, which is equal to 1 over z square plus b square the power n plus 1 along the contour C. Every time you have to write this line that what is your C here. C is a contour consisting of the real axis from minus r to plus r, following by this semicircle tau in the upper half plane from this plus r to minus r. Very clear? Whenever we have to integrate along the real axis, we have to write the variable in x. And when we integrate along this tau, we will write our variable in z. Very important to note this. Next. Now clearly fz has poles of order. Yes, what is the order of the poles? Let's check again. What is the power in the denominator? It is n plus 1. So poles are having order n plus 1 at z equal to, yes, this is, if you take the denominator equal to 0, then z is equal to iota b and minus iota b, right? Of which iota b lies inside the circle, this contour, and minus iota b lies outside this C, the contour. So clearly fz has poles of order n plus 1 at z equal to iota b and minus iota b, of which only iota b lies inside C. Now we have to calculate the residue of fz at this iota b, and the formula for that is 1 over n factorial limit. Yes, this is actually k minus 1 factorial. What is k over here? K is n plus 1. Very good. So the limit z tends to iota b. How many times we have to derivate? We have to derivate k minus 1 times. And what is k here? K is n plus 1. That means we have to derivate n times. You can check the formula which was given in the remark in the previous videos. So this is the power here is k, where k is n plus 1 into f of z. So this is equal to 1 over n factorial limit z tends to iota b, derivative with respect to z, and this is z minus iota b the power n plus 1. What is f of z? 1 over z square plus b square the power n plus 1. Can I write this in terms of factors? What are the factors? Z plus iota b and z minus iota b, because I need to cancel z minus iota b. So this is n plus 1, z plus iota b the power n plus 1. This is cancel out with this, and I have to derivate this 1 over z plus iota b the power n plus 1 n times, right? So this is equal to 1 over n factorial limit z tends to iota b d by dz, the nth derivative of 1 over z plus iota b the power n plus 1. What is the first derivative for this? I have calculated in pink color. The first derivative is you take the power in the numerator. This is minus n plus 1 over z plus iota b the power n plus 2. And then if you derive again, the second derivative is equal to, now of this minus 1, the power will be 2. So n plus 1 into n plus 2 over z plus iota b the power n plus 3. Now here when we derive second time, I'm having here n plus 2, right? Their power is 2. If I'm deriving second time, so this is 2, this is also 2 here, right? I have pointed out with orange color. And then if I derivate this with nth derivative, n times if I derivate, then I must get at the last bracket n plus n. If I am getting for the second derivative as n plus 2, so for the nth derivative I must get n plus n. And here if it is minus 1 the power 2 for the second derivative, then for the nth derivative I am having power minus 1 the power n, right? Divide by z plus iota b the power, yes, here. Now here it is n plus 2, the power is n plus 3, that means plus 1. Here it is n plus n, then the power will be this n plus 1, which is 2n plus 1. So I have written over here the nth derivative. Now this derivative I have write directly here, minus 1 the power n, n plus 1, n plus 2 up to 2n. This n plus n becomes 2n over z plus iota b. This will be 2n plus 1. 2n plus 1. Alright, fine. Okay. Shall I rub this? Alright, thank you. You can derive this separately on your own. Alright, what will be the next step now? This is equal to 1 over n factorial. Now I have to put limit z tends to iota b over here now. Let's put z equal to iota b. So this is minus 1 the power n, n plus 1, n plus 2 up to 2n over, this is iota b plus iota b will be 2 iota b the power 2n plus 1. Now I'm going to multiply and divide by n factorial because I'm having the reason for that. Let me first multiply and divide by n factorial. If I divide, this will be square, and if I multiply, this will be here n factorial, minus 1 the power n, n plus 1, n plus 2 up to 2n over 2 iota b the power 2n plus 1. Can I write this minus 1 the power n outside of this n factorial, which will be more clearer to you? Alright, it doesn't matter. Okay, so this will be 1 over n factorial square. Now what is n factorial actually? N factorial is n, n minus 1, n minus 2 up to so on, 2 into 1. This is n factorial. Alright, now what are the next terms in the bracket? N plus 1, n plus 2 up to 2n. So if I write the previous term for n minus 1 is n, just you have to add 1. Now I am adding 1 here, I will be getting the previous term to be n plus 1. So let me write here its previous term n plus 1, then it will be n plus 2, so on, n plus n, which is 2n actually. Can I write this whole as equal to 2n factorial? Yes. So I'm writing instead of this numerator as completely 2n factorial. So this is minus 1 the power n 2n factorial. This is why I multiply and divide by n factorial. Now you get 2 iota b the power 2n plus 1 in the denominator. Next. So this is equal to, if you solve, this is minus 1 the power n factorial whole square as it is, 2n factorial as it is. In the denominator I have adjusted this 2b the power n plus 1 and iota separately as iota the power 2n into iota, right? So this is 2n plus 1, sorry. Fine. This is bracket. This is minus 1 the power n over n factorial whole square. This is 2n factorial. This is 2b the power 2n plus 1. Now what is iota square? Iota square is minus 1. So can I write iota the power 2n as minus 1 the power n? Because iota square is minus 1 and here it is iota. Now this is cancelled with this. And I'm having finally, this is equal to 2n factorial over n factorial square to the power 2b the power 2n plus 1 into 1 over iota. Is it clear? Is it okay and fine? Alright. So we have calculated the residue of fz at z equal to b iota. Now I am using the Cauchy residue theorem here. So we get integral over c 1 over z square plus b square the power n plus 1 dz is equal to 2 pi iota times the calculated residue. And we have calculated this. So this is 2n factorial over n factorial square into 2b the power 2n plus 1, 1 over iota. Iota is cancelled out with this iota, right? And if you adjust this 2 with the denominator, you will be finally getting this as 2 pi over 2b the power 2n plus 1, 2n factorial over n factorial whole square. Nothing is to be done, just I have written this numerator and denominator as this product. So now this contour will be now splitting up this c along the real axis minus r to r. I have to write this in x, and then along the semicircle tau, and I'm writing this in variable z. So this is equal to this. Now I have to calculate this part first, and this part always comes out to be 0. The value comes out always to be equal to 0. So the formula is limit r tends to infinity, integral over tau 1 over z square plus b square power n plus 1 dz is equal to iota pi minus 0, limit z tends to infinity z into f of z. This is the formula. So this is equal to iota pi, limit z tends to infinity, z into f of z is 1 over z square plus b square the power n plus 1. So this is pi iota taking the limit. So here z square is taken outside from the denominator, and then the numerator will become 1 over z the power 2n plus 1 over denominator is z square plus b square the power n plus, this is, I'm sorry, 1 plus, because z square is taken outside. So this is 1 plus b square over z square. Very fine. So this is equal to 0. If you put limit z tends to infinity, this will be 0. Alright. Now let's put this 0, this value in 1. But before that, I have to define that I'm taking r tends to infinity. Right? because here we have calculated this integral with limit r tends to infinity. I have to define in 1 that first put r tends to infinity, let r tends to infinity in 1. Now I'm putting that value. We get, if you let r tends to infinity, this will become minus infinity to infinity, right? And this will be 0 for limit r tends to infinity. So this is dx over x square plus b square to the power n plus 1 equal to this. And now because I need the integral from 0 to infinity, but here it is minus infinity to infinity, what we do now? How to make it 0 to infinity? Alright, I know that this function is positive, it is even function too, right? As this is your even function, I know that for even function I can write this integral as 0 to infinity twice dx over x square plus b square the power n plus 1 is equal to 2 pi over 2b the power 2n plus 1, 2n factorial over n factorial square, right? So this is equal to, you cancel this 2 with this, and finally I'm getting 0 to infinity dx over x square plus b square n plus 1 is equal to pi over 2b the power 2n plus 1 into 2n factorial over n factorial whole square. Hence the result, the required proof. So this is a very beautiful example. Just practice this and one by one, step by step, you can solve. Very easy. Just you have to remember which pole lies inside or outside the circle, and then you have to calculate the residue at that pole, and after that apply the Cauchy residue theorem and then get your result. Alright guys, next time we will meet with some more assignments and examples which are very important. Thank you. Have a very nice and blessed day. God bless you.